In this video, we're going to talk about 7.2.2, which is Laplace transformations of derivatives. Let me show you a couple rules here that if we have Laplace transformation of y of t, I'm going to call that capital Y of s. And if we have the Laplace transform of the first derivative of y, then that's going to be equal to s times y of capital Y of t minus y of 0. So notice you have to have initial conditions here at t equals 0 to be able to use this. One more before I get to the generic form. So y double prime of t, when I take the Laplace transform of that, it's going to be s squared capital Y of t minus s y of 0 minus y prime of 0. So the higher the derivative is here, the more derivatives that I need defined at 0. I always need one less derivative defined than this derivative. So let's go ahead and try and write that generically. Laplace transform of the nth derivative of y of t is equal to s to the n capital Y of s minus s to the n minus 1 y of 0 minus s to the n minus 2 y prime of 0 minus dot 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 minus, and you run out of s's eventually, and you get down to y n minus 1, the nth minus 1 derivative at 0. So let's go ahead and take a look at some problems from the textbook, section 7.2, starting with number 35. And it asks us to have dy dt minus y equals 1. It tells us y of 0 is equal to 0. So the first derivative I have defined up here, s y of s minus little y of 0 minus, and then y we have defined right there, s. You can just look for the right-hand side, the Laplace transform of 1, look on your table, is 1 over s. So this was 0, I'm not considering it. I'm going to factor a y of s out and make this s minus 1. Capital Y of s is equal to 1 over s. So y of s is equal to 1 over s times s minus 1. I'm going to use partial fraction decomposition for this. So a over s plus b over s minus 1 equals 1 over s times s minus 1. A times s minus 1 plus b times s is equal to 1. When s is equal to 0, negative a is equal to 1, and a is negative 1. When s is 1, b is equal to 1. So y of s, capital Y of s, is equal to negative 1 over s plus 1 over s minus 1. That makes little y of t equal to inverse Laplace transform. Pull out the negative there, 1 over s, plus inverse Laplace transform, 1 over s minus 1 is equal to a negative 1 plus e to the t. Let's look at number 37 now. That is y prime plus 6y equals e to the 4t with y of 0 equal to 2. So s capital Y of s minus little y of 0 plus 6 capital Y of s is equal to 1 over s minus 4 when we Laplace transform both sides. So this is s plus 6 capital Y of s minus 2 is equal to 1 over s minus 4. S plus 6 capital Y of s is equal to 1 over s minus 4 plus 2 over 1 times s minus 4 over s minus 4 is equal to 2s minus 7 over s minus 4. So capital Y of s is equal to 2s minus 7 over s minus 4 times s plus 6, a over s minus 4 plus b over s plus 6 is equal to 2s minus 7 over s minus 4 times s plus 6, a times s plus 6 plus b times s minus 4 is equal to 2s minus 7. When s is 4, 10a is equal to 1, and a is equal to 1/10. When s is negative 6, negative 10b is equal to negative 19, and b is equal to 19 over 10. So capital Y of s is equal to 1/10 over s minus 4 plus 19 over 10 over s plus 6. So y of t is equal to 1/10 e to the 4t plus 19/10 e to the negative 6t. So now at number 39. 39 says y double prime plus 5y prime plus 4y equals 0, with y of 0 equal to 1, y prime of 0 equal to 0. So we have s squared capital Y of s minus s little y of 0 minus y prime of 0 plus 5s capital Y of s minus 5 lowercase y of 0 plus 4 capital Y of S is equal to 0 on the right-hand side. So let's see, Y prime term is 0, S squared plus 5S plus 4 capital Y of S. So that term, and that term are taken care of. And then we have minus S and minus 5 equals 0. So S plus 1 times S plus 4 capital Y of S is equal to S plus 5. Capital Y of S is equal to S plus 5 over S plus 1 times S plus 4. A over S plus 1 plus B over S plus 4 is equal to S plus 5 over S plus 1 times S plus 4. A times S plus 4 plus B times S plus 1 is equal to S plus 5. Letting S be equal to -1. 3A is equal to 4. A is equal to 4/3. Letting S be equal to -4. -3B is equal to 1, and B is equal to -1/3. So capital Y of S is equal to, A is 4/3 over S plus 1. B is -1/3 over S plus 4. Little y of t is equal to 4/3 e to the -t minus 1/3 e to the -4t. Look now at number 41. It says y double prime plus y is equal to √2 sine of √2t. It says y of 0 is equal to 10, and it says y prime of 0 is equal to 0. So we have S squared capital Y of S minus S y of 0 minus y prime of 0 plus capital Y of S is equal to, this is going to be √2 times √2 over S squared plus √2 squared. So this is going to be, let's see, y prime term is 0. This is S squared Y of S plus 1 Y of S, so S squared plus 1 capital Y of S minus S times 10 is equal to 2 over S squared plus 2. And we're going to have to add 10s to both sides. S squared plus 1 Y of S equals 2 over S squared plus 2 plus 10s over 1 times S squared plus 2 for S squared plus 2. S squared plus 1 capital Y of S is equal to 2 plus 10s cubed plus 20s over S squared plus 2. So capital Y of S is equal to 10s cubed plus 20s plus 2 over s squared plus 1 times s squared plus 2. Let's go ahead and drag this up to make some more room. So this is y s is going to be in the form of a s plus b over s squared plus 1 plus cs plus d over s squared plus 2 is equal to 10s cubed plus 20s plus 2 over s squared plus 1 times s squared plus 2. And we're going to make this s squared plus 2 times as plus b plus s squared plus 1 times cs plus d is equal to 10s cubed plus 20s plus 2. I'm going to have to expand everything out here. This is as cubed plus bs squared plus 2as plus 2b plus cs cubed plus ds squared plus cs plus d is equal to 10s cubed plus 20s plus 2. My s cubed terms are a and c. My s squared terms are b and d. My s terms are 2a and c. And my constant terms are 2b and d. So that gives me a system of equations that says a plus c. Second to catch up here. A plus c is equal to 10, and b plus d is equal to 0, and 2a plus c is equal to 20, and 2b plus d is equal to 2. So I'm going to subtract the first from the second. So I'm going to just change the order here. And same thing here, just swap the order here. There we go. So I can subtract more easily. So it's 10. And I have A equals 10, which makes C equal to 0. Here I have B equals to 2, and that makes D equal to negative 2. So we have 10s plus 2 over, I just want to make sure I have my denominators same way here as on my paper, s squared plus 1 plus CS plus D over S squared plus 2 is what my capital Y of S is. Let's put this over here a little bit, zoom out. Capital Y of S equals. So I have capital Y of S is equal to 10 times S over S squared plus 1 plus 2 over S squared plus 1, 2 times 1 here, minus 2 times, actually let's make this root 2 times root 2 over S squared plus 2 for the same reasons as before, that this is S squared plus root 2 squared, and the sine function needs to have the k up there, which is root 2. And so when I factor out a root 2 from 2, I'm left with a root 2, very much like how it looked originally. So I have y of t is going to be 10 cosine of t. And then I have plus 2 sine of t minus root 2 sine of root 2 t. We'll move on now to number 43. And that's going to be 2y triple prime plus 3y double prime minus 3y prime plus 2y is equal to e to the negative t. And we have y of 0 given as 0, y prime of 0 given as 0, and y double prime of 0 given as 1. And this is 2s cubed capital Y of s minus 2s squared y of 0 minus 2s y prime of 0 minus 2y double prime of 0 plus 3 times s squared capital Y of s minus 3 little s y of 0 minus 3y double prime of 0 minus 3s capital Y of s plus 3y of 0 plus 2 capital Y of s needs to be equal to 1 over s plus 1. And the y of 0 terms are 0. And the y prime terms are 0. And we have excellent. Okay. And y double prime is 1. Okay, so we have 2s cubed capital Y of s minus 2 times 1 is minus 2 plus 3s squared capital Y of s minus 3s capital Y of s plus 2 capital Y of s is equal to 1 over s plus 1. Gathering my like terms together here, 2s cubed plus 3s squared minus 3s plus 2 capital Y of s. I'm going to move that 2 to the other side of the equation and make it have a common denominator here with this other piece. Now you can use the rational root theorem to factor. I'm going to try and look to see if I can factor by grouping first. If I try and pull s squared out of the first group, I get 2s plus 3. If I try and factor a -1 out of the second group, I get -3s minus 2. That doesn't work, so let's try instead to group 1 and 3 with 2 and 4, and that gives me 2s squared minus 3. So that doesn't work. Let's try with 1 and 4 and 2 and 3. So that's s cubed plus 1. And that's, if I can pull out the 3s, that's s minus 1. That should work. So let me go ahead and just verify here that if s is I think it's a 1, 2, 5. Let me check my signs here. We have minus, this was a minus. That's what's wrong. That's why it's not factoring. This was a minus. Minus. And minus. Okay. My apologies. Fix the sign error and the problem. All right, so now we're going to, again, group 1 and 4 and 2 and 3. And I get 2s cubed minus 2 plus 3s squared minus 3s capital Y of s is equal to 1 over s plus 1 plus 2s plus 2 over s plus 1. This is going to be 2 times s cubed minus 1 plus 3s times s minus 1 capital Y of s is equal to 2s plus 3 over s plus 1. This is going to be 2 times s minus 1 times s squared plus s plus 1 plus 3s times s minus 1 capital Y of s is equal to 2s plus 3 over s plus 1. So this is s minus 1 times 2 times s squared plus s plus 1. Actually, let's put this all together. 2s squared plus 2s plus 2, and then plus 3s capital Y of s is equal to 2s plus 3 over s plus 1. And This is s minus 1 times 2s squared plus 5s plus 2, capital Y of s is equal to 2s plus 3 over s plus 1. This is going to factor a little more. It's minus 1, 2s, s plus 2 plus 1. 4 and 1 makes 5. Capital Y of s is equal to 2s plus 3 over s plus 1. And then we have capital Y of s is equal to 2s plus 3 over s plus 1 times s minus 1 times 2s plus 1 times s plus 2. I don't really like this 2 being there in the denominator because I know what form I'm going for here. So I'm going to multiply top and bottom by 1/2 and make this s plus 3/2 over s plus 1 times s minus 1 times s plus 1/2 times s plus 2. So that means that I'm going to split this into a over s plus 1 plus b over s minus 1 plus c over s plus 1/2 plus d over s plus 2 is equal to s plus 3/2 over all of this. And when that means that I have a times s minus 1, s plus 1/2 times s plus 2 plus b times s plus 1 plus s plus 1/2 plus s times s plus 2 plus c times s plus 1 times s minus 1 times s plus 2 plus d times s plus 1 s minus 1 s plus 1/2 is equal to s plus 3/2. And so I'm going to let s be equal to -1, and that gives me a times -2 times -1/2 is equal to 1/2. So a is equal to 1/2. And then I'm going to let s be equal to 1, and I have b times 2 times 3/2 times 3 is equal to 5/2. So get rid of the halves here, and I have 18b is equal to 5, and b is equal to 5 over 18. And I'm going to let s be equal to -1/2 to solve for c, and that is c times 1/2 times -3/2 times +3/2 is equal to 1. And so that gives me -9c is equal to 8. C is equal to -8/9. C negative 1/2. One half, negative 3/2, positive 3/2, 2/2 is 1. This is negative 9/8. C is 1. C is 8/9, negative 8/9, that's right. Okay. And then for D is when S is equal to negative 2. So we're going to have D times negative 1 times negative 3 times negative 5/2 is equal to negative 1/2. So get rid of the halves here, and I have a negative 15D is, sorry, this is negative 3/2. D is, S is negative 2. Let's just check that again. Negative 1, negative 3, negative 1.5, negative 3/2, yes. So negative 9D is equal to a negative 1, and D is equal to 1/9. All right, that's enough information for me to come back now and write y of t needs to be equal to inverse Laplace transform of a was 1/2 over s plus 1 plus inverse Laplace transform of b was 5/18 over s minus 1 plus inverse Laplace transform of c was negative 8/9 over s plus 1/2, and then d was 1/9 over s plus 2. So that's going to turn into y of t is equal to 1/2 e to the negative t plus 5/18 e to the t minus 8/9 e to the negative 1/2 t plus 1/9 e to the negative 2t. 1/2 e to the negative t, 5/18 e to the t, negative 8/9 e to the negative 1/2 t, 1/9 e to the negative 2t. All right, that's it, and that is everything for this video. You can see how you can use Laplace transforms to solve differential equations as long as you have the initial conditions for the function and the derivatives at t is equal to 0. It's a very powerful tool. This is helpful if you're going to program something with a computer. It can always use this technique, and it's very helpful. So this is pretty much the end of the ordinary differential equations class. There's some additional topics that sometimes we get to, sometimes we don't, but we for sure always get through 7.2. So I'm going to cover those other topics as I can, which are various topics from the rest of chapter 7, and to go back and talk about section 2.6 and section 9.1, which kind of go together, and that'll be it. So I'll do those videos as I have time, but this was the bulk of the course for right now. So I will see you for the next video whenever that is. It just may not be right away. So watch out for those upcoming videos on 7.3, 7.4, combined 2.6 and 9.1, which are really the same topic. And I may even go and delve into some other topics from the differential equations textbook that aren't normally covered in the 200 version of the course, but would be covered in a 400 level version of the course. We should be able to grab onto those and see how we could do things like solve systems of differential equations and things like that. Kind of a neat thing, but you need to know a little bit of linear algebra to do those, which is why it's a 400 level course. This could be taken alongside linear algebra. You don't need to know it ahead of time. You need to know linear algebra before you get into the topics that are in, I believe it's chapter 8. So I might come back and cover some of chapter 8 just for fun later, but that will be only for those of you who have a understanding of linear algebra already. All right, that'll be it. See you for the next video.